Hello and good morning everyone. We are from Group 3. Today we will present to you our group assignment, MOSFET scaling. Let's meet our group member. We have Hazi, Afi, Amir, Afai and me, Azira. The objective of this assignment is to simulate the N-channel MOSFET device structure using open source simulator, do characterization of IDVG and IDVD curve. For the first part of the simulation, this is the parameters that we used. In this part, we only change the channel length of the device. For device 1, the channel length is 50 nanometer, device 2, we change it to 40 nanometer, and device 3, 30 nanometer.
Okay, first of all, let's start with the device 1. Okay, this is the ID versus VD graph. From here, we can see that the higher VG value will produce the higher current. Next, this is the ID versus VG graph. From here, we can see that the higher VD value will produce the higher current. Next, this is the surface charge versus VG graph. We can see that the higher VD will produce the higher surface charge. Next, this is the analysis of the device 1. From here, we can see that the VTH value 0.45, the off current value 1.9 times 10 to the power of negative 12, on current 1.3686 times 10 to the power negative 4, the DIBL value 0.02633, the SS value 78.39. Next, let's continue with the result for the device 2. So this is the ID versus VD graph. So from here, we can see that the higher VG will produce the higher current. Next, this is the ID versus VG graph. So we can see that the higher VD will produce the higher current. Next, this is the surface charge versus VG. From here, we can see that the highest VD value will produce the highest surface charge. This is the analysis of the device 2. From here, we got the VTH value 0.41, off current 6 times 10 to the power negative 12, on current 1.668 times 10 to the power negative 4, the IBL value 0.05158, SS value 80.42. Next, let's continue with the result for the device 3. So this is the ID versus VD graph. From here, we can see that the higher VG value will produce the higher current. Next, this is the ID versus VG graph. The higher VD value will produce the higher current. Next, this is surface charge versus VG. So from here, we can see that the higher VD value will produce the higher surface charge. Okay. Next, this is the analysis of the device 3. The VTH value we get 0.31, off current 1.2 times 10 to the power negative 10, on current 2.353 times 10 to the power negative 4, the IBL value 0.07368, SS value 80.113.
Okay, next is the comparison for all the devices. So there are 3 devices which electrical properties, which consists voltage threshold, off current, on current, the IBL, and SS. So as you can see, the voltage threshold for device 1 is the highest, and for device 3 is the lowest. For the off current, also the same, which I off current for device 1 is the lowest. Okay, this is for I off, the device 1 I off is the lowest, and the device 3 is the highest I off current. For the I on device 1 have the smallest, and the device 3 is the highest. For I off, the current is gradually decreased from device 1. So for I off, from device 1 until device 3, the I off is increased, which make I off in device 3 is the highest. So for ion, from device 1 to device 3, the ion is increased. So for the IBL, the device 3 has the highest the IBL value. And for the last electrical properties is subspatial slope. So these properties for device 2 has the highest value. The next one is discussion part 1. So for the question 1a, find the electrical properties for all the devices, and all these devices well designed. So we have previously shown the table 4, which consists the electrical properties, voltage threshold, I-off, I-on, and the IBL for all the devices. So for this device are not well designed. From the simulation result, we can see that as we change the channel length, the electrical properties also will change. This is due to the short channel effects, which consequences arise whilst the channel length is at the same order of the magnitude because the depletion layer width of the supply and drain junction. The electrical properties changing is due to the short channel effects. So the parameter that could be changed to reduce the current leakage is to use a smaller oxide thickness, which it can improve ion and voltage threshold, and also reducing the substrate doping. Next is for question 1b. From your observation and result of device 3, what causes the IV characteristic behave differently from device 1 and device 2? Discuss this phenomenon and please suggest how to overcome this issue. So, as we know, the device 3 channel length is the shortest one from those 1 and 2 devices. So this device 3 can cause punch-through effect. So as we know, the I-on and I-off for device 3 is the highest among these 3 devices. This is because of the punch-through effect, and the barrier between source and drain is eliminated and lead to the large current. So this effect can be solved by implementing lightly doped drain transistor (LDD). This method will minimize the punch-through effect by doping the drain lightly, which can reduce the peak electric field at drain junction.
Next simulation for part 2, we use device 3 from part 1. We change the gate electrode. Device characteristic, which is we use gate electrode for device 1 is tungsten, device 2 is aluminium, and device 3 is molybdenum. Result for device 1, as you can see, the ID versus VD graph. When we apply higher VG, we produce the higher ID current. When we apply lower VG, it will produce lower ID current. For ID versus VG graph, when we apply higher VD voltage, and we get higher ID current. And when we apply lower VD voltage, and we will get the lower ID current. For surface charge versus VG current, when we apply higher VD, we produce the lower concentration of carriers, and we apply lower VD, we produce higher carriers concentration. For the analysis device 1, you can see we got VTH value is 0.773, I-off is 1.5 10 to the power negative 15 ampere, I-on is 1.2719 10 to the power negative 5 ampere, the IBL value is 0.0811, and SS value is 79.46. Result for device 2, we can see for ID versus VD graph, when we apply the higher VG, we get the higher ID current. When we apply lower VG, it will produce lower ID current. For ID versus VG graph, when we use the higher VD current, we will get the higher ID current. And when we use lower VD current, we will get the lower ID current. For surface charge versus VG, you can see when we use the higher VD voltage, it will produce the lower carrier concentration. And when we apply the lower VD current, we will get the higher carrier concentration. So for the analysis device 2, as you can see, we get VTH value is 0.23 volt, I-off is 9.5 10 to the power negative 10 ampere, I-on is 3 10 to the power negative 4 ampere, the IBL is 0.0964, SS value is 79.96.
Now we will move on to device 3, which uses molybdenum as its gate electrode. In the simulator, we set the work function to 4.6 electron volts. Here from the IDVD graph, we can see that for gate voltage equal to 1.2 volts, the drain current will keep increasing as drain voltage increases. Meanwhile, for gate voltage equal to 0.85 volts, the drain current increases until a certain point before it becomes constant. Lastly, no observable changes can be seen in drain current as drain voltage increases for gate voltage equal to 0.5 volts. This is the graph for IDVG. It can be seen that mostly throughout the graph, the drain current for when drain voltage is set to 1 volts is higher than when drain voltage is set to 0.05 volts. This is the graph for surface charge versus gate voltage. Throughout the graph, charge carriers for drain voltage equal to 0.05 volts is higher than when drain voltage equal to 1 volt. Table 7 shows the analysis for device 3. Threshold voltage equal to 0.75 volts, I off equal to 1.8 times 10 to the power of negative 15 ampere, I on equal to 1.683035 times 10 to the power of negative 5 ampere, drain induced barrier lowering or DIBL equal to 0.07895, sub-threshold swing or SS equal to 78.17 millivolt per decade.
Next is discussion part 2. So we will be discuss about voltage threshold, I off and I on, run in this barrier lowering, the IBL, and subthreshold slope, SS. Okay, this is the comparison part. For table 8, as you can see, there is a type of gate electrode and those electrical properties, which are voltage threshold, I off, I on, the IBL, and SS. So the first type gate of electrode, which is M plus polysilicon, which is from part 1 device 3. So there is the list of electrical properties from the part 1 device 3. So now I want to talk about the voltage threshold for tungsten, aluminum, and molybdenum. So as you can see that the voltage threshold for aluminum is the least from those 3 devices, and voltage threshold for tungsten is the highest values among them. So this is due to the fact that these metals have different work function. Okay, next is for I off and I on current. So the table shows for the aluminum has the highest I off and I on, and the tungsten has the least values of I off and I on. Next is drain induced barrier lowering values. So for N plus polysilicon, which is from device 3 part 1, the values of the IBL is lower than the tungsten, aluminum, and molybdenum. So for the values of the IBL for tungsten, aluminum, and molybdenum has the similar value. This is because the change of the electron does not affect the values of the IBL. Next is for subthreshold slope. So the highest value of SS is aluminum, and the least is molybdenum, which is 78.17. But the parameter that we want to measure is if the SS is near the value of 60 millivolt per decade. That is the best devices or the best properties that we should have. So for this, so molybdenum has the value 78.17, which is closer to 60 millivolt per decade.
Now we've come to the last part of this presentation video, which is conclusion. For part 1, I off in device 3 is greater than other devices because of short channel effect. The I on I off ratio will be low, resulting in punch through effect where there is high current leakage. Solution: implement lightly doped drain transistor or LDD. For part 2, based on device 3 for part 1, poly depletion occurs as transistor is scaled down and gate dielectric layer very thin. In order to solve this problem, metal gates electrodes can be introduced such as tungsten, aluminum, and molybdenum.